All right, so if we were to draw this in a graph, we can say that over time, as you heat something up, the rate of this line here would be evaporation, and then the rate of, pardon me, I did that wrong. This is the rate of condensation. If you're at a set temperature, the rate of evaporation is a constant. This is evaporation. But you see, once you seal it, once you seal your flask, like we did, all right, once you seal the flask, you don't have anything to condense yet, and it starts to. And eventually, they reach the point where the rate of evaporation is equal to the rate of condensation, and they become equal. So it's equilibrium. Okay? Not terribly difficult. Now, we can also talk about pressure in terms of, when we talk about this is kind of related to Dalton's law. So if I have a particular chemical, or this is a
mercury.
Mercury barometer, thank you. And then if I then throw some water in here, if you look carefully at this picture, there's just a skosh amount of water. And the way they measure this is they put some water in there and they measure the difference. Normally this is at 760 at 1 atmosphere, but when they do this with just a skosh amount of water, it pushes the mercury down a little bit. It pushes
water
down.
Vapor, by the way.
Yeah, water vapor. But you do put water liquid right here, and then that water liquid evaporates. And so you got little molecules of water in your tube right here. And as they press, they're actually pressing down. And at this particular temperature, I don't know what temperature we're at, it gives you a particular pressure.
Yep.
And if you do that with a different chemical, like ethanol, it gives a greater pressure. And if you use this chemical, it gives even a greater pressure. So they have different pressures. Now, something that's intriguing to understand about the different pressures, it relates to the last unit that we just talked about. It has to do with bonding. Okay, those liquids that give a high vapor pressure, like the diethyl ether, the pink one, or whatever color you want to call that, would have what type of a bond, Mr. Sams? Strong or weak?
They're going to be weak bonds.
Yeah, you see the ones with high pressures, high vapor pressures, have weak bonds, and those with strong bonds have low vapor pressures. Water is low because water is held together by hydrogen bonding.
Yeah.
Diethyl ether is held together by London dispersion forces, and therefore it has a very weak bond and therefore a high vapor pressure because it's easy to evaporate. If you think about it, if you want to evaporate a liquid, you got your beaker or whatever, and if it's easy to evaporate, that means it's got weak bonds. Now maybe you guys have filled the tank of your car with gasoline, and what do you notice when you're filling the tank?
When you open the cap,
yeah,
kind of go tss.
Yeah, that too, and also just you can smell it pretty strongly too, right? And that's because it has a high vapor pressure, and it evaporates pretty easily because it's held together by weak London dispersion forces.
Yeah, and things with high vapor pressures we call volatile liquids.
Yes, yeah. Actually, that's a good point. Somewhere, ignore this picture for just a moment. The word volatile. I-L-E. Volatile. Most people think of the word volatile to mean it burns, and that's not true. Volatile just means it evaporates easily. It means it's held together by weak bonds.
Right, which will in turn make it burn easier.
Yeah, if it is a burning chemical, but not all chemicals that are volatile are explosive, although quite a few of them are. All right. What happens in the process of evaporation? This is what we call the classical Boltzmann diagram. And basically, if I've got a T1 being a cold temperature, those molecules, because we say they actually have an average, this is the average kinetic energy, but some of them will have a very high amount of energy. These are the molecules that will evaporate. Now, if I raise the temperature, this is the same beaker, if you will, with higher temperature, I now have more molecules with enough energy to evaporate. And so at a higher temperature, it's basically the area under this curve is the higher temperature. All right?
Okay.
All right. And a graph that's kind of important to understand, we just talked about this. Of course, at higher temperatures, what happens to vapor pressures?
Goes up.
It goes up. So here's water right here. This is actually the actual vapor pressure at various temperatures. And so if I'm at 60 degrees Celsius, the vapor pressure of water looks like it's about 200 millimeters of mercury. Right here, right?
Yep.
But an interesting point that we should note here, at 760 millimeters of mercury, or the the pressure of water, or the atmospheric pressure at sea level, what's the interesting point here?
That's where the vapor pressure is equal to the atmospheric pressure.
And that would be 100 degrees.
That is the normal boiling point of water.
Yeah. Now, why'd you say the normal boiling point?
Normal boiling point refers to the boiling point at 1 atmosphere or 760 torr or at sea level.
Correct. And you see, folks, we live, those who don't know this, we live at a pretty high altitude, 8,500 feet. And I did the pressure this morning in my class, and we live at, our pressure today was 570, something like that.
Usually sits right around 570.
570 millimeters of mercury. And so if you were to take this ball game down right here, whenever it's, this comes out to about 92 degrees Celsius. So where we live, water boils at 92 degrees
Which
Celsius.
happens to be the perfect temperature to make a perfect cup of coffee.
Oh, really?
So when you boil water up here, you can put boiling water in your coffee, and it makes the perfect cup of coffee. Normally, it has to be a little bit below boiling.
But, well, it's 92 here in Woodland Park.
And I do like my coffee.
So that's what another way to look at this is how we can boil water. If I'm at the top of Mount Everest, I don't know the pressure of Mount Everest. Let's say for the sake of argument, it's 400 maybe.
It's probably lower than that.
I think it's lower than that. Whatever. Water would boil at 80 degrees, and so now you have actually kind of lukewarm water if you're making your coffee.
Yeah, stick your finger in your boiling water.
Yeah. Now this particular line is a curve, and guess what?
What?
It has an equation.
It does.
Mathematical
yes,
equation.
Yes, it does.
And so, in fact, if you plot a graph, this is the graph of vapor pressure versus temperature. If you wanted to draw a straight line, it will be the natural log of the vapor pressure versus 1 over the Kelvin temperature. Kind of confusing. And that gives you a straight line. And then it will have the equation y equals mx plus b. Now, but actually, y will be the natural log of the vapor pressure will be equal to the slope of your line, and the slope of your line is delta H.
VAP, heat of vaporization.
Actually, where would it be? That's actually the simplification one there. We're looking at our book, guys.
Oh, this one over here?
Yeah,
there
it is. It'll be
it's actually negative.
Of course, it's the negative slope. Negative delta H of vaporization, remember we talked about that, over R. Oh, there's that R.
Yep.
Times 1 over the temperature, that's in Kelvin, plus some constant.
Yep.
Okay.
So the natural log of your vapor pressure is your Y. Your M is negative delta H over R times 1 over T. That's also part of M. And then, that's X, sorry. And then plus B is your constant there.
And that's just your constant. That's your B. Okay. I think I have it out. So, I think we've already said this, but how do you boil something up?
Either heat it up.
Heat it up.
Or lower the vapor pressure.
Lower
or the atmospheric pressure.
Pressure. All right, we already did our demo. Okay, so here's the equations. Actually, I typed
look
them
at
out.
that.
How's that for a while? And actually, if you rewrite this equation when you're comparing two vapor pressures, this is the more important equation right here.
Yes.
And it has a name that I was just, I think
it's the Clausius-Clapeyron equation.
The Clausius-Clapeyron equation made by Mr. Clausius.
Yes, so we have Clausius-Clapeyron, and then we had the Henderson-Hasselbalch back when we did acids and bases. So.
Yeah. All right, so now let's do a mathematical example. So if we've got a vapor pressure of water at 25 Celsius, it's at 23.8 torr. The heat of vaporization is this number. What is the vapor pressure of water at 50 Celsius? So we're going to use this second equation. This second equation, the Clausius-Clapeyron equation, is really the more important equation. So you basically have two temperatures and two vapor pressures. So the torr, this is 25 degrees Celsius. I'm going to call that T1. 23.8 I'm going to call VP1. All right, and the heat of vaporization is given to me, and then this is going to be T2. All right, so now I need to just plug all these things in. So the natural log of, is it 1 over 2 or 2 over 1?
It's 1 over 2.
So I'm going to say the natural log of 23.8 over x is what I'm looking for, is equal to, now here's an important part. You're going to take this 43.9 kilojoules per mole, and I'm going to type in 43,900 over 8.3145 times 1 over, I always get this mixed up, T2. Now T2 is 50 Celsius, and 50 Celsius in Kelvin is
298. Oh, no, sorry, it's 323.
323
sorry,
minus 1 over
298.
298. This, by the way, gets rid of the constant. The constant's not in this equation. And then you just plug this into your solver and you solve for it. I'm not going to teach you mathematically.
Yep.
I would, by the way, do natural log of
you use solver?
Oh, yeah, 23.8 divided by x, parentheses, minus 43,900 divided by 8.3145 times 1 divided by 323 minus 1 divided 298.
And I didn't use the solver, and I got the answer. It's 93.7.
And does that make sense? We went to a higher temperature, 50 degrees Celsius.
So we should have a higher pressure.
And our pressure was 23.8 at 25, so at 50 it should be a little higher. And actually, we could actually go back to that graph, by the way, I just had up a little bit ago. We were, what, 50 degrees Celsius? So at 50 degrees Celsius, water is saying it's 93. All right, I can live with that. That looks like about 93, doesn't it? Yeah. All right, so that's how you do those problems.